Talk about big O notation, and we are going to work this using a merge sort example. So let's say I gave you a 10-digit list with the numbers 5, 3, 8, 9, 1, 7, 0, 2, 6, and 4, and 4. The way that merge sort works is that you split the numbers a half at a time. So this is my first level. Just gonna mark it with the and and I'm going to mark it using italics. Just undo that. Let's just delete this and that. So I'm gonna mark it using italics. So that's 1, and this should be 2. There we go. This using italics. 1, and then level 2. What is that going to look like? Level 2 is going to look like this piece. So we have 5, 3, 8, 9, 1 as one set, and then 7, 0, 2, 6, 4 as another set. And we keep breaking these down by 2, and eventually we'll get pairs. And it is possible to have singletons, and singletons would just be compared to itself. So in this case, we'll have 5 and 3 as a pair being compared. We'll have 8 by itself, 9 and 1, 7, 0, 2, 6, and 4, 2 by itself, 6 and 4. Okay, so this is the point of inflection. The way merge sort works is that once it gets pairs or singles, it just starts ordering. So this then becomes 3 and 5, 8 is just by itself, and this is 1 and 9. You have 0 and 7, 2 by itself, and then 4 and 6. Okay. Next, we'll leave that there. So that's the breakdown. Next, when it eventually comes back together, you'll have you start merging the ordered pairs. So when it's all said and done, you'll have the numbers 0, 1, 2, all the way up until you get to 9. So those are our 10 digits. Now notice what I want to point out here is that we originally began with 10 digits. So we'll call n the number of inputs, right? So n being the number of our inputs, we started off with n items. Now, in theory, as this scales for very large numbers, what you end up having, because we're dealing with pairwise comparisons, remember that for this merge sort, you end up having the number of rows you would get is log n where of course n was the number of inputs. And in computer science, when we talk about log without specifying the base, it is assumed that it is the number 2. So let's just go ahead and write that for clarity. Just put the 2 there, right? And so this array, if you will, this array has n times log of n items. Now, it is worth noting that when I did the inflection, that we didn't only just break down to pairs, but we also had to re-merge it as well. So when we're dealing with big O notation, if it's 2 times n times log of n, we don't count any constants. So this constant, a constant times this, will just be simply just reduce to just n times log of n. Okay, that's how big O notation works. Now I want to show a special case, and that special case actually deals with what happens if we didn't choose pairwise. We went from pairs to triples. I think I need to click this one. Maybe not. We went from pairs to triples. In other words, we wanted to break down the merge sort in threes or thirds. Okay, so the number of inputs won't change. We'll still have n inputs, right? But the number of rows is going to be what? Our number of rows is going to be log of n to the base of 3. Why is it to the base of 3? Because we're breaking these down into thirds, right? We're comparing thirds and not breaking it down into pairs, which would be more intuitive, right? So, but watch this. We know that in the case where we're dealing with a triplet, let's say element 1, E1, E2, E3, right? So this would be 3, this would be 2, and this would be 2 and then 1. So we'll move the 2 here, and we will move the 1 there. All right, so in those elements, I can't just do a pairwise comparison. So this is going to take some work. We know that log of n to the base 3 is smaller than log of n to the base 2. So the temptation is to think that breaking it into thirds would be faster than doing a merge sort that breaks it into pairs. But because we can't do a triplet wise comparison, we actually end up scaling the actual inequality check. But watch this. Watch what happens mathematically. So consider the case. So the number of the operations that has to be done here gets factored by log of log of 3, excuse me, log of 3 to the base of 2. Okay. And where did we get the 2 from? The 2 actually comes from a pairwise comparison. So even when we're dealing with a triplet, we need to break this down to do a pairwise comparison. So there's the factor of operations gets scaled by this number. Now, if we just took the array as we originally thought of, maybe I should do this in a different color. Okay, well, that's not gonna work, but this is fine. Okay, so in theory, we thought that it would just be our normal n times our log of n to the base of 3. Now, since I had to scale this by another log of 3 to the base of 2, watch what happens. Mathematically speaking, I can take, if I want to convert the log of n to the base 3 in terms of log of 2, we can do that. So we have an identity. So that I can rewrite this as I'll take the log of 3 to the base 2 on the outside. Yeah. And then I have it times n. That doesn't change. Right? But log of n to the base of 3 can be written as the ratio of the log of 2, log of n to the base of 2 divided by log of 3 to the base of 2. And essentially what you're doing here is if you have a log of a number to a given base and you want to change the base, you write the log of the number to the new base divided by the log of the of the original base to the new base. So this is equivalent. And what ends up happening is that log of 3 to the base 2 actually cancels. And then we end up with our theoretical limit of n times log of n to the base 2. So whether you do triplets or thirds or quadruples or whatever, the fastest you can ever get a merge sort or any type of sort is n times log of n, assuming base 2. And anything that would not be a pairwise comparison would scale up the number of calculations. Therefore, before you actually work out your final your final result for big O, if you want to put in terms of log 2, it actually approaches the theoretical fastest of n times log of n to the base 2. I'll say this one more time. That when we looked at our first case, right? I did an example. We looked at our first case. The rule of thumb here is that you multiply the length by the width, which would give you the number of call stacks, which is time complexity. And that is n times log of n in big O notation. Now, but this was a pairwise comparison. So what we then try to do is that we try to look at thirds. So I still have n. Oh, but can it get faster if I start doing log of n to the base 3? That should be faster than n times log of n to the base 2. But since we're not doing pairwise comparisons, we actually have sub operations. Think of it as nested loops, if you will, that increase the number of calculations. But when it's all said and done, using our logarithm identity, this can still approach the theoretical optimized limit of n times log of n to the base 2. All right, thank you and happy coding.